Moving our vector study from lines to planes, we are going to partake in a bunch of videos now exploring the idea of planes and regions in a plane and determining Cartesian and vector equations. So firstly, let's be clear on what a plane is. So there's we see there a sketch of a plane, and basically a plane is a smooth surface. So when we say plane, one idea we might better relate to is this idea of a smooth flat surface. So a normal, we can see a normal in this first diagram. Vector n is a normal. More generally, with even outside of the study of vectors, normals are talked about. A normal is basically a line which is perpendicular to a surface, or we could say a plane. It's at 90 degrees, and you can see in this plane here we've got n, which is the normal. So if you can, it's kind of hard to represent 3 space with a 2 space diagram, but you can probably see what the creator of this graphic was trying to do. So n comes out at right angles. If I was to look at a side-on profile of that, purely side-on, we would see n come out like that if we looked at it from a different orientation. Now, the idea of a normal has many applications, and this video is not about the applications. It's about how we wrangle vectors and how do we determine Cartesian and vector equations, which puts you on your way to using them in many applications, both in the physical world, real life situations, but also in purely mathematical situations as well. So that's the little journey we're on. Because we can have infinite number of normals coming out of all the different points on the surface, on the plane, we could say there is a normal exists. So for every point on the plane there exists a normal. Okay, fair enough. So going back to our little profile, if all of these other normals coming out, they're all in the same direction, aren't they? Yeah, that might be important, because some of our previous studies talked about this idea of direction vector. And direction is important in general when we're talking about vectors, so we'll make note of that. So what we've said, basically, there's basically no unique vector or normal vector. I'll insert that word normal. There's no unique normal vector for a given plane. We should note that. Thus, for normal n, we also have k times n parallel, where k is the elements of a real number set of real numbers. So in other words, if n is normal to the plane or perpendicular to the plane, so is kn, where k can be any real number. Moving from normals to planes to equations of planes, we can see that we have a different diagram here of a plane with some vectors drawn on it, and we're going to develop on the idea that a plane in 3 space, so a plane in 3 space can be described by two vectors. Which is awfully handy, isn't it? And this three-space plane can be described by, firstly, a position vector, now you can see that position vector there because it connects a certain point A with the origin O. So position vector, let's call that A. So that's of point A, which is on the plane. Has to be on the plane, it's irrelevant otherwise. And also a vector N, normal. You can see him there. Okay, a vector N, which is a normal to the plane. Alright, so it's normal to the plane. We can use those two to describe a three-space plane. Okay, now the derivation needs something else. So we've got another point P. Okay, so let P be another point, not A, alright, that's on the plane. It's a crowded plane, isn't it? All planes are crowded with points. Haha, they're overbooked. Haha, that's not very funny. If you've got better vector jokes than me, well, send them my way. I'll steal them from you. As long as you don't use jokes that have the phrase in them, what's the point? Okay, that's not funny and it's not very productive. Okay, so we can see that R is the position vector. Okay, so R a position vector of that other point P. Connecting the 2 points that we've been talking about, A and P, we get the vector AP is yielded, and we can use lowercase r minus lowercase a for that vector. Now, this is perpendicular to the normal. Okay, so N. Alright, because it goes along the surface of the plane, and we know the normal comes out perpendicular. So, alright, fair enough. And when you're talking perpendicular, we're very often talking about dot product of vectors. So, r minus a that we just got there is a vector itself, and it's perpendicular to n. So what's going to happen when we dot those two together? We'll get 0. Okay, and using the distributivity of the scalar product or the dot product, we get r dot n minus a dot n. That equals 0, which suggests that r dot n equals a dot n. This is the actual vector equation of the plane. So note that r dot n equals a dot n. Now, not just vector equations, we're going to chase the Cartesian equation now. So if we represent that line OP, the position vector of P, which we called R before, if we represent that in a general sense in a Cartesian form, we'd get xi plus yj plus zk. And we'll note that. So if we've got R equals that and N equals this, we use the basis that we just achieved up here, the vector equation of the plane, to develop the Cartesian equation of the plane. So calling that vector equation of the plane number 1, from 1 we can develop what we need to develop in terms of the Cartesian equation. So writing down 1 again, it's worth writing down a few times. You want to learn this, it's important. And so supplementing this with the actual Cartesian components, we've got It doesn't matter what order you write, it's commutative anyway. So I'm just going to write it down as this, using the dot product definition, and that will still equal to a dotted to n. And that's essentially it. So the actual widely used form of the Cartesian equation, which we virtually have now, is written or used as such. The a dot n is actually called something, it's called, referred to as k nominally, okay, where k equals a dot n. Oops, a dot n. So let's identify that. And by the way, if you're thinking parametric, we're not going to touch the parametric equations. They're not helpful for us at this point in the game. So there we have the Cartesian equation of the plane. So in this video we've looked at normals to the plane in introduction to that, and we've derived the generic form of vector equation to the plane, and likewise with Cartesian equation of the plane.